Lesson 6, explosions. A bullet leaves the muzzle of a rifle with a velocity of 6 times 10 to the 2. That's 600, and I'll probably type 600 in my calculator because it's less writing. If the 3-kilogram rifle is held very loosely, with what velocity will it recoil? You might recall about a month ago I showed you when we were looking at forces come in pairs, some guys firing a really, really high-powered rifle, and it had a lot of recoil, because if the rifle applies a force to the bullet, what does the bullet do? Applies the same force to the rifle. That was looking at it in terms of forces. Now we're going to look at it in terms of momentum. This is an explosion. How many objects are there in this question? Okay, this is a job for conservation of momentum. I have some students ask me, Mr. Duick, how do I know when it's impulse? How do I know when it's conservation of momentum? If there's 2 different objects, it's probably going to be conservation of momentum, unless the question blatantly says, find the impulse of the first object. So I'm going to start out by saying the sum of all the momentum we started with equals the sum of all the momentum we finished with. Is there more than one mass in this question? Yeah. Yesterday I said I'm going to be lazy but organized. You know what? Rather than mass A and mass B, how about I call this B for bullet and R for rifle? A little easier to keep track of that way. Okay. Before we pull the trigger, because that's what causes the explosion, before we pull the trigger, what's moving? The bullet, the rifle, both, or neither? Ooh. If nothing is moving, what's my initial momentum? It's kind of weird. Bang! We pull the trigger. After we pull the trigger, what's moving? The bullet, the rifle, both, or neither? How do I know both? Well, they definitely told me the bullet is moving, and they want the recoil velocity, so they must both be moving. Stuck together or separate? Hopefully separate, otherwise something's gone really wrong. So I'm going to say, after I pull the trigger, I'm going to have mass of the bullet, velocity of the bullet, and mass of the rifle, velocity of the rifle. What am I trying to find? VR? Yeah. How am I going to get that by itself? I guess I can move that. How would I move that over? Yeah, in fact, that's just going to give me plain old negative MBVB. And then how will I move the mass of the rifle over? That's going to be the velocity of the rifle. What's the negative telling me? If the bullet goes forwards, the rifle recoils backwards. If the bullet was fired north, which way will the rifle recoil? South. Here, I'll just leave a negative, I think, in my answer. Also, what's heavier, the bullet or the rifle? Be obvious. I think the rifle is going to recoil slower than the bullet left. Significantly slower, but it's still going to be there. Negative 0.06 600 divided by 3. I think I can do this in my head. It's going to be negative 600 divided by 3 is 200. 1.2? 0.12. Am I totally off? I got the wrong number. What do you get? Oh, 12. I had the decimal in the wrong place. meters per second. Now, they didn't specifically say next to the word velocity in brackets, magnitude and direction, but there's the direction, backwards. Is that all right? So for an explosion, it's really the same as conservation of momentum. If both objects are at rest before things blow up, what's your initial momentum? 0. You know what your final momentum is still? 0. If you add up the momentum of both of these, the bullet's momentum was its mass times its velocity. The rifle's momentum was its mass times its velocity, and sure enough, you get 0. Still works. The law of conservation of momentum holds. I used to work at a summer camp for a few summers as a camp counselor, and one of the things I did is I taught canoeing. And I saw the following happen fairly often. Spencer is sitting in a canoe, floating on the water next to the dock. He decides to stand up and step sideways out of the canoe and onto the dock. Why does Spencer get wet? Why will he end up in the water? I saw this happen all the time, and I would just giggle. Or, very, very similarly, if you've ever tried, when you're, say, horsing around in a pool or in a lake, standing on something that floats, like an inner tube, why is it that when you try and dive off, you belly flop? Yeah. Okay, right now, what's the momentum of Spencer and the canoe if they're at rest? 0. If Spencer wants to have some momentum to his left, which way must the canoe move? Who has a bigger mass, Spencer or the canoe? Probably the canoe. So which one's going to move faster? Who has a bigger mass? I think Spencer has a bigger mass than the canoe, actually. And the canoe is going to move faster. And either Spencer's going to end up doing a dock split and end up in the water, or he's just going to end up in the water. How do you get out of a canoe? If you're by a dock. Yeah? Okay? No. There's a couple of ways. First of all, what's my momentum right now? You keep your momentum 0. You turn your body sideways like this. What's our momentum still? If I can sit down, now I've got some friction between myself and the dock. That'll hold me in. Or you pull yourself in if you're really, really clumsy. And that'll work as well. But what you don't do is just stand up and step off. Man, have I seen people either on the shore do the same thing and the canoe goes out from underneath them, or by a dock do the same thing. Is that okay? So how are we going to write this? Initial momentum is 0. If Spencer steps to his left, the canoe must move which way? And canoe has smaller mass than a person. Canoes weigh less than a person. So it'll have a bigger what? I heard someone say it. If it's got a smaller mass, think in terms of momentum. Think in terms of momentum. Think in terms of momentum. Yep. It'll move out faster than Spencer steps left. And again, this is why if you've ever tried diving off of an inner tube, what happens? The inner tube shoots out from underneath your feet, and you usually end up pretty spectacularly belly flopping, not doing a graceful dive. This is a really neat video that I have. Let me just do this for a second, Mr. Dewick. Name accidentally. Weird, I know. Physics, momentum, what's it called? 0. Oh yeah, this is really, really neat. What's the momentum of the boy and the surfboard right now if they're at rest? Everybody? So what must their final momentum be? Still. So if the boy walks forwards, the surfboard must Absolutely. Oh, and I think the surfboard has a smaller mass than the boy. So actually the surfboard moved a little fast. Let's see. Actually, looks like they're about the same because the boy doesn't look like he's moving much at all. These might have almost identical masses and be almost perfectly canceling out. Is that all right? Example 3. You may have tried this on an ice skating rink. If you've been on ice before, a boy and a girl are standing in the middle of a frozen pond. They're going to put their hands together and they're going to push off of each other as hard as they can and go backwards. First of all, forces come in, so each one will experience the same force. With what velocity will the boy move off with? I'm going to argue, Nick, that this is technically an explosion. It's a slow explosion, but this is a job for conservation of momentum. Can we use, how about G for girl, B for boy? Okay, so I just put a subscripted G on that M and a subscripted B on. Since they gave me a picture, I'll label the picture. Beforehand, what's moving? What's the initial momentum? Okay. 0 equals, after the explosion, what's moving? The boy, the girl, both, or neither? Stuck together or separate? Mass girl, velocity of the girl, plus mass boy, velocity of the boy. What's this asking me to find? Gershon, can you get that by itself? I guess with that 0 there, we'll just minus that over. Yeah. So read me the equation in your head, can you? V boy equals negative 60. Oh, Gershon, do you want that 2.4 there to be negative or positive? Because we do have opposite directions, so we should have decided which way is positive. Do you want this to be negative or this to be positive? Sorry? Positive. So and I'm okay with that. You decided for this question to let left be positive. So if we get a positive answer, that will be left. If we get a negative answer, that will be, okay. We're going to get a negative answer, which is to the right. What do you get? Can I do this one in my head? Maybe. 60 over 45, that's the same as what? 4 over 3. So 2.4 divided by 3 is 0.8. 4.8? Negative 3.2. Duick, you're in a slump right now. Or 3.2 meters per second to the right. And the direction was pretty easy because the picture kind of told me it was to the right. Ooh. Ah. Nick, what does B want me to find? What's another word for impulse, everybody? Change in momentum. So what's change? Oh, that's that delta. How do you think I'm going to find the impulse of this boy? Force times time? How do you know? I don't see a force or a time here. So how am I going to find impulse? Mass times change in velocity. Yeah, I'm going to go mv final minus mv initial. Ooh, even better. What was v initial? That's a bonus. It's going to be M45. V final, technically negative 3.2. Which is what? Marcus, what'd you get? units, or you could say Newton seconds, but since we use mass times velocity, I'd probably go with that one. Okay. What's the negative telling me? What direction if they asked for a direction? To the right, right? Right. What's the impulse of the girl? Put your pencils down. You all know the answer already. Positive 144, because whatever momentum the boy lost, the girl gained. This is the law of conservation of momentum. Whichever changed in one direction, the other one was the opposite change. Momentum is conserved. So the impulse of the girl, you can pick your pencils up now, I'll call it PG, and I'll call this one PB, is positive 144 kilogram meters per second. And I guess that's to the left. And why is that the case? That's true because forces come in, and because they were part of the same collision, time must be the same. So force times time must be the same. They must have the same impulse. Opposite impulses, but same magnitude. Yeah?
Yeah, it's negative to the right.
Fine. That's why actually I put it in brackets. I didn't put an at. I was hedging my bet saying, for what it's worth, it's to the right. Okay. It's a good point. Also, I hadn't said magnitude and direction in brackets, and so I was wondering, I was trying to remember, because I haven't taught this lesson for a couple of years now, did I want direction in here? Whatever. Oh! If the push lasted for 0.25 seconds, Lena, what's D asking me to find? With what? Force. I could probably go F equals M. Probably could. But what did I just find in part C? What did I just find in part C? Is there a version of impulse that has force in it? Does it have time in it? Oh, let's use that. Force is impulse over time. 144 over 0.25. I'm slumping so much, I better do the math on my calculator, Mr. Dewick. 576 newtons. Okay. So next time you're on a skating rink with a friend, try this. Oh, let's blow up a space capsule. I think this got a couple more and then we're done, right? Yeah, we're nearly done. Good. A space capsule consists of a 2,500 kilogram main capsule and a 1,500 kilogram probe, like in the little picture there. Suppose the space capsule is traveling forwards at 120 meters per second when an explosion occurs between the capsule and the probe. After the explosion, the probe moves forward at 280 meters per second. Ooh. Raj, what does A want me to find? Okay. It said speed. I think I'm going to find velocity and just not reported direction. By the way, did the probe speed up or slow down? What do you think happened to the main capsule then? Because momentum has to be conserved. If the probe gained momentum, this must have lost momentum. So I can already tell you it's probably going to be an answer less than 120. Built-in error check. Is there more than one object here? Is there an explosion? Conservation of momentum. The sum of all the momentum initial equals the sum of all. Mr. Dewick, do I have to write that every time? No. But on a test, if you write that and it is a conservation of momentum question, I will give you a half mark just for that, because I will say, yes, you've recognized that this is conservation of momentum. What would be a good letter to use for capsule? What would be a good letter to use for probe? Let's go with that instead of A and B. Before the explosion, what's moving? The capsule, the probe, both or neither? Stuck together or separate? Stuck together. So I think it's going to look like this. You know what? I think I'm going to do one line over here because I'm going to run out of room. It's going to be mass of the capsule, mass of the probe, V initial. Boom! The probe explodes. The capsule explodes. The craft explodes. Afterwards, what's moving? Separate? Okay. Mass capsule, V capsule, mass probe, V probe. And Raj, I guess they want me to find that bad boy. Okay. What's going to drop down like a domino? I agree with you totally. So it's going to be mass capsule plus mass probe V initial. Then I guess I need to move this over. I think you would. Final step? Boy, that's messy. Yep. That'll do it. Alrighty. 2,500 plus 1,500 times 120 minus 1,500 times 280 all over 2,500. Someone wants to put their phone on vibrate? Because next year that'll cost you 10 bits. Ooh, I got to put that whole thing in. Okay, I need to open up a bracket for the top and then open up a bracket. I'm totally wrong. Oh, I got a times sign in there. Now, what am I? No, what did I do? Oh, I did, yeah. I multiplied the masses. Well, that was silly. How about I add the masses? But the nice thing was I could tell that I was totally wrong by looking at the answer. Ooh, get 24? So that probe picked up almost all of the momentum. The capsule lost almost all of its momentum. Not all of it, but a lot of it. It said speed, but if you ask me for a direction, still forwards. If it was moving backwards, could it move backwards? Yeah, the explosion could have been so big that the capsule could have been blown backwards. How would I know it was blown backwards? What would I have got as an answer? Negative. Yeah. I don't know, because it's the velocity. Thank you. I did a momentum. I'm in a slump this morning. What's the magnitude of the impulse given to the probe? Oh, that's easy. Impulse is change in momentum. That's going to be m probe v final minus m probe v initial. Did they give me the final velocity of the probe? Did they give me the initial velocity of the probe? Easy peasy. It's going to be 1,500 times 280 minus 1,500 times 120. That's just straight plug and chug. I get 240,000. This one is kilogram meters per second, right? Whew. Is that okay, Callie? Same thing. Am I right? People nodding? All right, what's the impulse given to the capsule? It lost 240,000 kilogram meters per second. A couple more, we're done. Turn the page. Or next page over. No, are we turn the page? Flip it over. There you go. Mountain climbers use nylon safety ropes due to their tendency to stretch considerably under stress. Use principles of physics to explain why mountain climbers would want to use stretchy ropes and not ropes that were all rigid. Yeah. Shock, I like the concept, but shock is not a physics word. Can you say it in terms of physics concepts? Okay. Time increases. What does that do? If we think about it in terms of impulse, and okay, if we reduce the force, what does that do? What does that make smaller? F equals what? Does it make the mass smaller? No. This goes back to what you said a couple of days. What does damage? Okay. There are situations where you might want a rigid rope, not for a safety rope if you're a climber. You want one that has some flex to it. How does conservation of momentum help explain why it's so difficult for firefighters to hold hoses that are ejecting large amounts of water at a high speed? Has anybody here used a fire hose before? Not a garden hose, but a fire hose? Anybody here in the fire academy? Okay. They got some kick, yes? In fact, when it's full out, you're probably having to lean into it and apply a constant force to hold it in place. In fact, if it gets tiring. Yeah? Okay, why? Okay. What's coming out of the hose? More generically, in terms of a physics concept, what's coming out of the hose? I'm thinking about something that starts with letter M. Mass. Does the mass have some velocity? Okay. So is the fire hose giving the water an impulse? First of all, here's the nozzle. Is the water behind the nozzle in the hose traveling really, really fast? Or does it gain its speed when it leaves the nozzle? Ooh, that's a good question. Convince me. Okay. So I think in terms of conservation momentum, hose gives water lots of momentum. You know what? Let's say this, lots of forward momentum. Well, if momentum is conserved, the water gives the hose lots of what? Okay? Water gives hose backwards momentum. And in terms of change in momentum, if we think of it in terms of an impulse, force times time, you're having to apply force. You can also think about it in terms of forces. The hose applies a force to the water, forces come in, water applies a force back on the hose. Okay. Here's a nice little thought puzzle. The diagram below shows two pop cans of unequal mass. In fact, it looks like one is mass M and the other is mass what? Twice as heavy. An explosive charge is detonated between them. Boom! And the cans fly apart. What can you tell me about their velocities after the explosion? Yeah. Ooh. Will M be moving twice as fast as that? Why? I agree. So let's say that. M, little m, Mr. Dewick. Let me M. Okay, right click. Let's do this. Here's going to be the workaround. Space, space, little m has twice the velocity of 2m. Let's see if we can do a proof. Before the explosion, what's the momentum of everything? So let's write down 0. They explode. Boom. So if you're wondering, when we're talking about conservation of momentum, the equal sign represents the collision or the explosion. And one side is the before, one side is the after. I guess we're going to have little m, its velocity, plus 2m, its velocity. That's really confusing with lots of m's and 2m's. I should have gone with a and b, but that's okay. Let's get this v here by itself. I think it's going to be negative m vm equals 2 m v 2m. And as a matter of fact, I think in this case, is there an m right here? Is there a little m right here? They're going to cancel. If I divide by m, we're going to cancel. We're going to cancel. We get this. Negative velocity of m equals twice the velocity of 2m. What did you say? Can m has twice the velocity of? But we should have added one more thing. Right? Yeah. What's your homework? Number 1. Okay. Number 2, these are just a bunch of collisions. They're in picture form. So you need to find the missing velocity. That's the one that's labeled V apostrophe. What do you think this picture is trying to say? The two masses stuck together, as opposed to here they did not. So you can try number 2. Let's go number 4. I skipped 3. 5 is good. 6 is good. 7 is good. I'll skip 8. I'll skip 9. $11, so I skip 10. I'll pass on the nasties this year. They're cool, but I'll pass on them. Because I also know many of you still are working on the homework from last day.